Okay, so just so tonight's agenda. So we're gonna kind of start out with chapter 19 things. Really, I think on Monday we covered all of chapter 19, at least kind of the hard material, kind of the calculation based material, the most of the questions that would be covered in exam questions. I didn't really talk much about the last video. It was mostly applications of nuclear chemistry. It doesn't mean that you couldn't theoretically be asked about it. However, it's not a main topic of the material. Um, if anything, maybe one question. But again, it's more the professors, and I'm sure you've caught on through the 2 semesters, now being at the end of the second, that they like to teach you the material, but they also like to show the application of the material to real life. And so that last video on nuclear chemistry was mostly showing why we care about chapter 19. Medical imaging is one of the bigger applications of it. So that's mostly what the last video was about, which is why I'm not really going to talk about it. But yeah, so we're going to go through a couple of examples from chapter 19. Then, based on what people suggested as kind of the activity on Monday, we're going to review chapters 12, 15, and 18. Specifically in chapter 12, we're going to look at half-life, the integrated rate law, and catalysis questions. That's actually kind of perfect because I wanted to go through a nuclear chem rate example tonight as well. So that actually kind of perfectly fits another chapter 19 example that I wanted to go through. Then we're going to go through a buffer and titration question. A lot of people kind of asked about the equivalence point and past the equivalence point. So that's what my, what I actually say. We're going to spend a little bit more time on that and clearing up that. And then we're going to talk about electrochemistry in water. I don't have an example for that, but I tried to break it down and at least make the theoretical portion of that make a little bit more sense. Because I think for the electrochemistry in water, really what your professors would want you to get out of that is kind of the theoretical side of it. I think if it came up in like a mathematical type of question, it would be rather simple. They're really going to test, do you just kind of understand electrochemistry and water in general? So we're going to break that down. And then again, at the end, I'll talk a little bit about the final, how to kind of prepare for it, what I'm going to do to try to help you guys prepare for it, and etc. Okay, so I just wanted to start out with just one quick slide as review of what we kind of covered on Monday. So I love this chart. It shows lots of the different types of decay that we learned about on Monday. And so it shows what alpha, beta, gamma decay are, positron emission, along with electron capture. It does leave out protons and neutrons, but we kind of know what those are already. And yeah, so it just wanted to give you guys a minute to look over this in case you aren't that familiar with this material yet. It'll kind of give you a general idea. So just a quick reminder, whenever we see alpha decay, we're going to lose 2 neutrons and 2 protons from our parent nucleus, right? So this is our parent nucleus. We're going to lose 2 protons, 2 neutrons, and what's left with our daughter nucleus is going to be a nucleus with 4 less mass units and 2 less protons, right? A represents mass, which is protons plus neutrons. We assume that they all have a mass of 1. And Z represents number of protons. Okay, so alpha decay, we lose 2 protons, 2 neutrons. In beta decay, what actually happens is we lose a high energy electron. And when you lose a high energy electron, that means you actually lose it from the nucleus. And this occurs by a neutron in the nucleus. And that neutron is going to be converted into that high energy electron, which is lost, and it's converted into a proton. Okay, so basically what happens is a neutron is converted into a proton. Therefore, our mass is unchanged, right? Because a neutron has a mass of 1, so does a proton. So that should have no net mass change. but your number of protons is actually going to increase by 1. And I would definitely note that beta decay is the only type of decay where we actually see, sorry, I'm going to make a little correction to that. There are only 2 types of decay where the number of protons will increase by 1. Okay, it's beta decay, where protons increase by 1 and mass does not change. The only other one where we could see an increase in protons is if we actually just add a proton to the nucleus, right? But if you added a proton to the nucleus, your protons would increase by 1 and your mass would also increase by 1, okay? In gamma decay, we actually don't lose any mass or any protons. It's actually just energy that's lost, right? So you go from a higher energy state or an excited energy state down to a lower energy state, okay? And you're just going to release what we call gamma rays, okay? And that's gamma decay. We have positron emission. In here, this is kind of almost the opposite of beta decay, right? Instead of in beta decay, we go from a neutron to a proton within the nucleus. During positron emission, what happens is a proton within the nucleus is actually going to convert into a neutron, and it's going to release a positively charged particle that has the same mass of an electron. Okay, and so here, our mass isn't going to change because we're going from a proton to a neutron, so 1 atomic mass unit to 1 atomic mass unit, but our number of protons is going to decrease by 1. Okay, and electron capture is very, very similar to positron emission. The only kind of different part of it is that you're actually going to absorb an electron, and instead of emitting a positive particle, we are going to emit X-rays, okay? But in terms of our mass and our protons, the change is going to be the identical between electron capture and positron emission. Okay, so now that we've done that little review, we're going to get into some examples. Okay, so I just want to do another mass defect example. And so here we have an electron that reacts with a nucleus, causing decay. During this decay, the parent nucleus splits into 2 identical nickel-68 nuclei, a neutron, an alpha particle, along with X-rays, right? So all of that is on kind of like the product side. So I want you to write the balanced equation for this decay. I'm asking what type of decay events occurred, and what is the binding energy per nucleon? Okay, and that's in MeV per nucleon. Okay, and all of these values that I gave below would be given to you. Okay, you're not expected to know any of these values. Okay, and then I said, do not include the incoming electron in mass defect calculations, which by mass defect, I'm talking about binding energy. Okay, because, yeah, don't include that electron that's absorbed and reacts with the parent nucleus. Okay, so I first want to start out by writing the balanced chemical equation. And just realize that your final exam is going to be multiple choice. So if a question like this did appear, it would probably be as several multiple choice questions, right? This would probably constitute about 3 or 4 multiple choice questions. I just incorporated a lot into this one question. Okay, so at first I just wrote my generic formula, right? I knew that I had a parent nucleus that I'm just going to write as X. An electron's going to come in and react with this parent nucleus to produce 2 nickel nuclei, each with a mass of 68. That's what nickel 68 means. Plus a neutron. So a neutron we represent with N. It has a mass number of 1 and it has 0 protons. And it's also going to create an alpha particle, right? So an alpha particle has a mass of 4. It has 2 protons, and because it has 2 protons and no electron, it has a positive 2 charge, and it also is going to produce X-rays, right? That was said. Okay, and so when you're trying to balance nuclear equations, it's essential that you make sure that the mass number and the number of protons are the same on each side. Okay, we don't really care about the charge, right? So the alpha particle charge of +2. We don't really care about that. It's just mass number and protons that we care about. Okay, and so I'm going to find how many of these we have on our product side, right? Because we know everything about our product side, but we know relatively nothing about our reactant side. Okay, and so to find the total mass number of the product side, I did 2 times 68 because we have 2 nickel atoms or nuclei, each with a mass number of 68, plus a mass number of 1 from our neutron, plus a mass number of 4 from our alpha particle, for a total mass number of 141. Okay, so 141 is our total mass on the product side, and therefore must be our total mass on the reactant side, right? So parent nucleus X has a total mass of 141. Now we have to try to find the identity of that parent nucleus, which we're going to do through the number of protons. Okay, so again, protons must be the same on reactant and product side. So in terms of protons, we have 2 times 28 protons, and that comes from nickel. Okay, nickel by definition, when you look on the periodic table, will always have 28 protons. That will never change for nickel, okay? And so because we have 2 nuclei of nickel, it's 2 times 28 plus 2 protons that we see in our alpha particle. Okay, we don't need to include the neutron because it has 0 protons. And so when we add up the total number of protons, it comes out to 58 protons, which when we look on the periodic table corresponds with Ce. Okay, and so that tells us the identity of the parent nuclei. Now that we know the mass and the identity of our parent nuclei, we can plug that in to write our balanced equation, right? So Ce-141 will react with an electron to produce 2 nickel-68 nuclei, plus a neutron, plus an alpha particle, plus the X-rays. Okay, now the second part of this question asked, what are the different types of decay that we're seeing here? And so the big two that I really want you guys to catch, is alpha decay and electron capture, right? We know alpha decay occurred because we produced on the product side an alpha particle, right? Which only occurs when alpha decay occurs. So alpha decay had to occur if we're producing an alpha particle. Now, during this reaction, an electron came in to react with our parent nucleus, and a product was X-rays. Okay, that is an indicator that electron capture also occurred. Okay, and so that one you also hopefully picked up on, that electron capture was occurring, and so X would have gained a proton and then split in half. Okay, and then lastly, a neutron was produced. And that's just because a neutron's on the product side. That one was, it's kind of there. That one's not as big of a main decay that we would see. Okay, now the second part of this is the very calculation-based portion of this type of question, and it's asking about the binding energy per nucleon. Okay, so remember that a nucleon is just a proton or a neutron. Okay, a proton or a neutron is a nucleon. Okay, and so here, when we start with Ce-141, we have 141 nucleons, which are, again, protons or neutrons. But we'll use that a little later. Okay, so for binding energy calculations, you're going to want to split up this problem into before and after. Okay, and so before, on the before section, we're going to focus with our parent nucleus, which is Ce-141. Okay, now Ce has, again, by definition, 58 protons. And if it has a mass of 141 and it has 58 protons, it has to have 83 neutrons. Okay, so we know how many protons there are, we know how many neutrons there are, and there's no indicated charge on Ce. So we're going to assume it's neutral, right? And remember that neutral atoms have equal numbers of protons and electrons. Okay, so that would tell us that this also has 58 electrons. Okay, so knowing how many protons, electrons, and neutrons we have, we can take those numbers and multiply each of those particles by their respective masses. Okay, so a proton is 1.0073 atomic mass units, an electron is 0.00055 atomic mass units, and a neutron is 1.0087 atomic mass units. Okay, and so when we do that multiplication and add them all together, right, our original CE nucleus should have weighed 142.1774 atomic mass units. Okay, now we're going to focus on the after portion. Okay, and so you'll see, or you would have seen in the question, that I actually gave you a mass for the nickel nuclei. And the reason why I gave you that mass is because there must have been some deviation from the expected mass. Okay, so we were told that each nickel nuclei was 68.5363 atomic mass units, and there were 2 of them for a total mass of 137.0726 atomic mass units. Okay, now we also produced a neutron and an alpha particle. Okay, now I didn't tell you anything about the mass of the neutron and alpha particle, and so we would base these masses based on the real masses of a neutron and protons. Okay, so one neutron would weigh 1.0087 AMU. And an alpha particle, because I didn't tell you otherwise, you're going to assume is equal to the weight of 2 neutrons plus 2 protons. Okay, which when you did that math would come out to 4.0320 atomic mass units. Okay, and so you add these all together and you find that kind of on the product side or on the after side, your mass is 142.1133 atomic mass units. Okay, so as you can see from before to after, there is a slight difference, right? There's a slight mass defect, right? That's what we call it. And so we can actually solve for that mass defect by taking the mass from before and then subtracting the mass from the after section, right? Kind of from the product side. And what we find is the mass defect, or the mass lost when converting from reactants to products, is 0.0641 atomic mass units. Okay, so that amount of mass was actually converted into energy during this process of decay. Okay, once we find the mass defect in terms of AMU, we can find the binding energy in terms of MeV, right? We're told that 1 atomic mass unit is 931 MeV. And so we take that number, we multiply it by the mass defect, 0.0641 AMU, and we would find that the binding energy is about 59.68 MeV per atom. Okay, but I didn't ask for just binding energy and MeV. I asked binding energy per nucleon. And so to find that, we take the total binding energy that we just solved for, and we divide it by our 141 nucleons, right? Which is basically just the mass number of CE. And that gives us our final answer. So in the chat, somebody asks, is this the same equation as E equals mc squared? That's a little tough. I would say likely. However, I'm a little unsure because I am not the most adept at MEV calculations. So I actually got this from Dr. P's slides, and he actually doesn't break this calculation down into E equals mc squared. He just takes AMU and multiplies it by this conversion factor. Okay, so I'm a little unsure. Typically, when I do E equals mc squared, that's to solve for the energy in terms of joules per atom. And so if you look at Monday's session, I did that calculation out. as E equals mc squared. But again, Dr. P in his lectures, when he did E equals mc squared to get the binding energy in terms of joules per atom, he again just multiplies it by some random number or some seemingly random number and doesn't really say where he gets that from. And so I know that doesn't completely answer your question. So in the chat, it said, should we do the math out like this if they ask for binding energy instead? So again, that's kind of hard to answer. It depends on what they tell you, right? So if they tell you, like I did in this question, I said 1 AMU is 931 MeV, right? So that conversion right there probably did come from E equals mc squared, right? But you don't have to plug it into that equation because I actually already did that I already did that conversion for you, right? But if they tell you, you know, the speed of light, which is c, and if they tell you the mass, they would give you kilograms per AMU would be a conversion factor they give you, then you'd plug it into E equals mc squared, right? So again, kind of look at Monday's example. Yeah, I think what your professor did, Dr. P, is he kind of already did E equals mc squared to get this conversion factor and plugged it in. I don't love that he did it that way. However, that's kind of how they did it. So I guess it depends on what conversion factors they give you, right? If they give you MeV per AMU or joules per AMU, then they already did the E equals mc squared portion. You just do the mass defect times that conversion factor to get your answer, right? If they give you the speed of light and some number that's in kilojoules per AMU, then they want you to plug all of that into E equals mc squared, if that makes sense. Does that make sense? Okay, cool. Okay, so to move on to our next example, it's relative stability, right? So this is definitely something I'd expect to be maybe a multiple choice question that you see on your final, maybe even two, because in lecture they did go over relative stability to a fair degree. So for this, we have two small examples, and it's just which of the following is more or the most stable and why, right? So PT 208, which I believe is platinum 211, and AU, which is gold 211. Okay, that's the first example we're going to look at. And then our second example is HG, which is mercury 216, or U, which is uranium 264. Okay, so for this first example, what I did is I first referenced my periodic table to find how many protons each of these elements have, right? So platinum has 78 protons, and gold is actually right next to it and has 79 protons. Okay, and I'm actually sorry, I actually made a little mistake here. I just didn't really do math correctly, right? And so what I wanted you to do for this first one, and again, I apologize for the mistake, is it was basically looking at the trend of even, odd, and odd, odd. And what that's referencing is the number of protons and neutrons that you have, right? So if you have an even number of protons and an even number of neutrons, right, there's a high chance that that nucleus is relatively stable, right? If you have an even amount of neutrons or protons and the other one, whether it's neutrons or protons, there's an odd number, right? That has a lower chance of being stable. And then if you have an odd number of both protons and neutrons, that will actually have the lowest stability relatively, okay? And so what this should actually be to make this example correct, you should actually have 212 as your mass number for gold. Okay, so just change this to 212 and this would be correct. Okay, because platinum, right, it has 78 protons, and if you were to solve for the number of neutrons, there would be an even number of neutrons. I believe it would be 130 neutrons. Okay, so you would have an even number of protons and an even number of neutrons. Okay, so you'd expect that to be the most stable. Okay, now if you had platinum with 211 as the mass number, you would have an even number of protons, 78, but you would have 133 neutrons, which is an odd number of neutrons. So you'd expect this to be less stable. And again, pretend this mass number should have been 212. Okay, I apologize for that, 212. And so if you had a gold with a mass number of 212, you would have 79 protons, which is an odd number of protons, and then you would have 133 neutrons. Again, if this was 212, which would be an odd number of neutrons. And so again, odd, you'd expect that to be the less stable. And again, I apologize, it should be 212. Okay, so that's one of the big trends that you should be aware to compare stability of these nuclei. Okay, now let's look at the second example, which was looking at uranium versus mercury. Okay, so mercury was 216 as its mass number, uranium 264. Okay, now as a very general rule of thumb, right, as the number of protons increases, typically that isotope is more unstable. Okay, so as a general rule, we would expect uranium to be more unstable compared to mercury. Okay, but another really good measure of stability is our neutron to proton ratio. Okay, and that's also how I justified my answer for this second question. So mercury, by definition, has 80 protons, and uranium, by definition, has 92 protons. Okay, so based on the mass of both of these nuclei and the number of protons, right, we can find how many neutrons each of these nuclei had. So mercury would have had 136 neutrons, and it has 80 protons, so if we were to find that ratio, it's about 1.7. Okay, now for uranium, it has 92 protons, meaning that there was 172 neutrons based on its mass number. We're going to take the number of neutrons, divide it by the 92 protons, and find that the ratio is 1.87. Okay, now the closer this ratio is to 1, right, the more stable the isotope is as a general rule of thumb. Okay, it's not perfect, but as a general rule. And so based on this, the neutron to proton ratio, along with the trend that as the number of protons increases after iron, right, really this trend only occurs after iron, the one with less protons and the smaller ratio will be more stable. Okay. Are there any questions on this problem? Okay. Then let's just look at a decay example. So I think this is a pretty good example of how you could see decay in like a multiple choice question, right? So this is actually kind of two parts, but I'm showing a two-step decay, and I have like an X and Y variable. And I'm basically asking you to fill in the missing information. So what is X? What is Y? And hopefully W doesn't mess you up. That's an element, that's tungsten. Okay, so basically we're finding X and Y. And so as a multiple choice question, you can, it could be what is X? And then you'd have A, B, C, D. And you try to think of what would be the correct, thing. Okay, so in this first decay, right, in this first step of decay, we have Re 190, and it's going to go to a X, whatever X is, but it also underwent alpha decay. And I know this is an A. I didn't know how to put in the alpha symbol, but A here is supposed to be alpha decay, and you can kind of tell that by the loss of mass equal to 4 and the loss of protons equal to 2. Okay, so here we have Re, and the mass of this is again 190. And this is going to go to X plus our alpha particle, right? We showed alpha decay here. Okay, so the first step that I did was look at the table, try to find Re, and what I found is that the atomic number, or the number of protons associated with Re, is 75. So I wrote that in. Okay, now because during this transition we underwent alpha decay, right, my X compared to Re is going to lose a mass equal to 4, and it's going to lose 2 protons, right, because that shows up as the alpha particle that is lost. Okay, and so if my original mass for Re, that nucleus, had a mass of 190, then the mass of X has to be 4 less than that, which would be 186. Okay, now if Re also has 75 protons, and 2 of those are going to be lost into my alpha particle, that means X has to have 2 less protons than 75, therefore it should have 73 protons, which is represented by Ta. Okay, and so X here would is Ta 186, right? And you can write this 73. It's also not required because, again, Ta by definition will always have 73 protons. Okay, so that was the first step. Now the second step, or the second decay, we have Ta, which is going to further decay into tungsten 186 and Y. Okay, and I apologize if you think that the alpha particle should have been considered here. I didn't mean for that to be the case. This is kind of how I wanted the second step to be written. Okay, I didn't want you to account for the alpha particle. That kind of would have been lost into space, and this Ta would have undergone further decay. Okay, so here, right, Ta 186 is going to be converted into W, which is tungsten 186. Okay, and so because they both have a mass of 186, we know that there was no mass change during this decay step. Okay, but when we compare these two elements, Ta has 73 protons, while W, tungsten, has 74 protons. Okay, so we actually increased by 1 proton during this step. Okay, and there's only one type of decay that we associate with no mass change and an increase in the number of protons, and that's beta decay, meaning that Y needs to be a beta particle. Okay, so a beta particle can be written as beta 0, -1, or you can see it as E 0, -1, with the E representing the high energy electron that's released during beta decay. Okay, are there any questions on this? This is kind of, for the most part, our chapter 19 review for the night before we go into kind of our review chapters. And if people don't mind signing in right now to indicate that as well, whether there are questions or not. Okay, so some people wanted me to go through chapter 12, the integrated rate law, half-life, which does come to one more example that we will have from chapter 19. Okay, so just remember that half-life is the time that it takes for the reaction to reach the halfway point, right? And what that means in terms of our initial reactant is it's the time it takes for half of our reactant to disappear. Okay, and this is actually a very common unit to see in nuclear chem, right? Because we have radioactive isotopes, and typically we talk about half-life in how long it takes to break down these isotopes, right? And I actually believe that that's one of the topics discussed in the final video for chapter 19. It's about how to do, you can do like dating. So, you know, if you find radioactive isotopes in rock, right, you can kind of calculate, or based on the half-life, you can calculate how old that is. And so that's one use of half-life. We also have the integrated rate law. Okay, and so basically what the integrated rate law is used for is you start with an initial amount, like an initial concentration of reactant, and it allows you to calculate after a certain amount of time how much of that reactant is remaining. Okay, that's what the integrated rate law is used for. After X amount of time, how much of my reactant is remaining. Or if I started with X amount and I now have Y amount, how long did it take for that process to occur? Okay, that's integrated rate law. Oh, and I don't know. Oh, that said half-life over, so I'm sorry, it just randomly says ha. I labeled this as a half-life slide because that's what I wanted to go over. So this is a chart that you would recognize from chapter 12. It's pretty much your best friend from chapter 12, right? Remember, we basically went over zero order, first order, and second order reactions in great detail back in chapter 12. Okay, and so this is helpful because it shows the integrated rate law for each, zero, first, and second order. It also gives us our half-life equations for all three of these types of reactions. Okay, now in terms of chapter 19, nuclear chem, right, we actually really only care about first order reactions. Okay, whenever we're looking at nuclear half-life, all of our radioactive compounds are going to follow first order kinetics, meaning they're all first order reactions, and those are the equations we should use. Okay, so whenever you're dealing with radioactive compounds and their half-life, the equation is going to be T1/2, which is the time for half-life, is equal to the natural log of 2, which I believe is 0.693, divided by K, our rate constant. Okay, so this will always be the the half-life equation that we use for chapter 19. Okay, if you're not dealing with radioactive isotopes, right, it could just be a normal chapter 12 question, which means it could be zero, first, or second order reactions. Okay, but again, if it's chapter 19, radioactive nuclear half-life, you're going to always use the first order equation. And then the integrated rate law for these compounds is what's shown below. The natural log of NT equals negative KT plus ln of N naught. Okay, now K is our rate constant, right, in this equation. T represents time. N0 is just the initial amount of the isotope that we have, and NT is how much of that isotope we have remaining after a certain amount of time, right? T. That's why it's NT. Okay, so let's look at an example of this in reference to chapter 19, or yeah, chapter 19. So you have 16.2 grams of radioactive isotope, and they run into a pond through runoff. The half-life of this isotope is found to be 7.82 years. And so how much of the isotope would be remaining after a century, right, or 100 years? Okay, and so again, really this is going to be extremely similar to problems we saw back in chapter 12. right? So we were given the half-life. And so we're going to use this equation in order to solve for K, our rate constant. Okay, so again, our equation is T1 half, that half-life, which is 7.82 years, is equal to the natural log of 2 divided by K. Okay, and so when we solve for K, it comes out to 0.0886 years to the negative first. Okay, that's the units on it, but. Okay, so now that we have our rate constant, right, we can use that in our integrated rate law to eventually solve for NT, which is, again, the amount of radioactive isotope remaining after the century. Okay, so here is our integrated rate law for first order reactions. And so I'm going to plug in K, which is, again, what we saw for above, 0.0886. For time, I'm going to plug in the century, 100 years. And for N0 or N0, I'm going to put my initial amount of radioactive isotope, 16.2 grams. Okay, and from here, it's just a bunch of algebraic manipulation. But when you solve for NT, it's going to come out to 0.0023 grams, which is equivalent to 2.3 milligrams. Okay, and so that's how much radioactive isotope would still be remaining in the pond after 100 years. Okay, are there any questions on this before we jump into buffers and titrations? That'll probably be the majority of our discussion for the rest of the session. Okay. Oh, I'm sorry, I forgot about the catalysis. Okay, so activation and catalysis. So remember that activation energy is the energy barrier between it's the energy barrier that you kind of run into when trying to convert reactants to products, right? So if you don't have enough energy to overcome that activation energy, no reactants will be able to become products. And that's kind of the reason why we see some reactions happen very quickly and easily, and oftentimes other reactions are very difficult to occur and may occur extremely slowly or potentially not really at all. And so we also learn about catalysts. And so catalysts allow reactions to occur more quickly. And how they do this is by actually lowering that energy barrier, right? They're going to decrease the activation energy. Okay, and there's just some general notes on there, right? They're not used up in a reaction, therefore they're also zero order. So if you change the concentration, it's not going to change the reaction speed. Okay, but I think what people wanted me more to talk about is the typical catalysis problem. Okay, and so the typical problem, you'll be given a reaction that is run without a catalyst, so the uncatalyzed reaction, and it'll also be run with a catalyst. Okay, so typically what they'll do is they'll run the uncatalyzed reaction at different temperatures. Okay, so at each temperature, you are going to have a different rate constant. Okay, and because these are both the uncatalyzed reaction, the energy barrier, that activation energy, is going to be identical. Okay, and so this information for the uncatalyzed reaction, you could plug in to this first equation that I wrote down here, right? As you can see, this equation incorporates two equilibrium constants, with each of these associated with a different temperature. Okay, now this question will also give you a catalyzed reaction that will have the same rate as the uncatalyzed reaction at the higher temperature. Okay, and the key to that portion is that the catalyzed reaction and the uncatalyzed reaction at the higher temperature will actually have the same rate constant, or the same K value. okay? And typically this problem ends by being told that the frequency factor is constant between the different reactions, which allows you to assume that A, that frequency factor in the second equation is equal to 1, and the natural log of 1 is equal to 0. So you can basically just ignore that portion. That's the significance of that last portion. Okay, so let's look at an example. And again, my example, I tried to fit to a T, how I just put that classic example up. Right, so we have an uncatalyzed reaction with an activation energy equal to 56 kilojoules. When this reaction is run at 100 degrees Celsius, the rate constant is 0.00541. This same reaction is also run with a catalyst. When run with a catalyst, the rate at 25 degrees Celsius was seen to be equal to the rate of the uncatalyzed reaction at 200 degrees Celsius. And so what they want you to solve for here is the activation energy of the catalyzed reaction. And again, here's that statement at the end, assume the frequency factor is the same. Okay, I've never seen a catalysis question where this last statement is not included. Okay, and so for this problem, we're going to start with our uncatalyzed information first. Okay, so for our uncatalyzed reaction, our activation energy was 56 kilojoules, which is equal to 56,000 joules. Okay, now we had a rate constant, which I'm going to label as K1, that is equal to 0.00541. And this was the rate constant at 100 degrees Celsius, which I'm going to label as T1. And 100 degrees Celsius is 373 Kelvin, right? Because when we use this equation, we're going to have to plug in our temperatures in terms of Kelvin. Okay, now we also ran this reaction, or theoretically would run this reaction at 200 degrees Celsius, which is 473 Kelvin. Okay, but we are not sure what the rate constant is at that temperature. And so we can use this formula to help us solve for that K2, right? So the formula is ln K2 divided by K1, which K1 is this 0.005 number, is equal to the negative activation energy in terms of joules, so 56,000 joules, divided by R, which is a constant, it's that 8.31 joules per mole Kelvin constant, times 1 divided by T2, which is 473 Kelvin, minus 1 divided by T1, 373 Kelvin. Okay, now we can go through from here. It's a lot of algebraic manipulation, and we can eventually solve for K2, which comes out to 0.2466. Okay, so that is our rate constant when we run the uncatalyzed reaction at 200 degrees Celsius. Okay, now you may notice if you look at your equation sheet that the equation I use is slightly different than the equation on the equation sheet, right? The equation on the equation sheet is positive activation energy over R, and then it's 1 over T1 minus 1 over T2. Okay, I do negative activation energy over R times 1 over T2 minus 1 over T1. Okay, whether you use, no matter which equation you use, right, you're going to get the same answer, right? It really has to do with this negative sign or the positive sign. That's why it's slightly different. Okay, but again, if you plug in these numbers, you should get the same exact answer. Okay, and I checked that. Okay, now that we solve for K2, which is again our rate constant of the uncatalyzed reaction at 200 degrees Celsius, we can actually apply that to our catalyzed reaction, right? Because I said that the rate of the uncatalyzed reaction at 200 degrees Celsius is the same as the rate of the catalyzed reaction at 25 degrees Celsius, right? That means that their rate constant is the same. Okay, so now I'm going to turn my attention to the catalyzed reaction. And for this, I'm going to use the equation ln K equals ln A minus activation energy over RT. Okay, now again, the rate constant K that I'm going to use here is the K2 rate constant that I solved for, so 0.2466. Okay, I'm going to assume my frequency factor A is 1. My R is that 8.31 constant, and my temperature, 25 degrees Celsius converted to Kelvin, is 298 Kelvin. Okay, from here, I'm going to solve for activation energy. It's just algebraic manipulation. And you'll find that activation energy is positive 3,467 joules, which is approximately equal to 3.47 kilojoules. Okay, and that makes sense, right? We're saying that the activation energy for the catalyzed reaction is about 3.5 kilojoules, while the uncatalyzed reaction, its activation energy is 56 kilojoules. Okay, so as you can see, when we use the catalyst, it lowered the activation energy, which is what we know a catalyst to do. Okay. So if there are no questions on that, we're going to jump into titrations. So again, in this course, we see strong titrations and weak strong titrations, right? So you can have a weak acid titrated by a strong base or a weak base titrated by a strong acid. So the example that I have is going to be a weak acid titrated by a strong base. Some key principles to titration problems is that the equivalence point is when the moles of H plus equal the moles of hydroxide. Okay, that will always be our equivalence point. Okay, and what happens is the H plus or protons will react with free hydroxide to produce water. Okay, and then kind of the big reminder that I would let you guys know about titration problems is that you should always use moles. Okay, always start out by using moles in titration problems. Okay, so this is a very classic titration question. We're going to have hydrozitic acid, so just kind of a weak acid, right? You might not know what hydrozitic acid is, but we know it's not a strong acid, therefore it must be weak. And this is going to be titrated by a strong base, which is barium hydroxide. And so what is the pH when the following amounts of barium hydroxide are added, right? 40 milliliters, 50 milliliters, and 52 milliliters. Okay, so my first step for a titration question like this would always be what I do at the very top here, right? I would first solve for how many moles of weak acid do I have. So hydrozitic acid, I'm just gonna denote with HA. We have 300 milliliters of that. It's 0.1 molar. And so when I do that math out, I have 0.03 moles of HA, hydrozitic acid. Okay. What I then do is look at each separate part, A, B, and C, and I solve for how many moles of hydroxide do I have from barium hydroxide. Okay, and so in part A, 40 milliliters of 0.3 molar barium hydroxide. When we solve for just moles of hydroxide, right, not barium hydroxide, but just the hydroxide itself, we will have 0.024 moles of hydroxide. In part B, we have 0.03 moles of hydroxide, and in part C, we have 0.0312 moles of hydroxide. Okay, and you'll notice that each one of these points represents a different scenario, right? Remember, if our moles of weak acid is greater than our number of moles of strong base hydroxide, we are before the equivalence point. Okay, so A is before the equivalence point. If the number of moles of weak acid and strong base hydroxide are the same, right, we are at the equivalence point. So part B corresponds to at the equivalence point. And then in part C, we have more moles of hydroxide than our amount of weak acid. And so we are past the equivalence point. Okay, and we're going to solve all three of these scenarios differently. So that's why it's really important to figure out which scenario you are in. Okay, so anytime you're before the equivalence point, which is part A, you should first write your balanced chemical equation. So I always suggest taking your weak species, which in this case is a weak acid, and I always react it with water. Okay, this is always my reactant side for a titration problem. So when a weak acid reacts with water, it's going to produce hydronium and conjugate base. Now my initial amount of weak acid is the 0.03 moles that we solve for at the top, right? That won't change from one part of this question to the next. Okay, so that'll be the initial in your ICE table. Now the change is represented by the amount of hydroxide we add in part A. Okay, so we're adding 0.024 moles of hydroxide in part A, which means that's going to represent our change. Okay, and we're going to add that amount to our products. How do I know this? Well, the whole idea of titrations is your equilibrium is going to shift to produce, in this case, it's going to produce hydronium, which is going to neutralize that hydroxide that you're adding. Okay, so our change, we want to be plus 0.024 moles of hydronium so that it neutralizes the hydroxide. Okay, so it's going to be plus that amount to products, minus that amount from reactants, and at equilibrium, we will have 0.006 moles of weak acid and 0.024 moles of conjugate base. Okay, anytime you are before the equivalence point, you should have some amount of weak acid and conjugate base at equilibrium. Okay, you should have some amount of each. Okay, and so because we have some amount of weak acid and conjugate, we can actually solve for the pH using our Henderson-Hasselbalch equation, which is pH equals pKa plus log of base divided by acid. Okay, and so in order to use this equation, we need to find our pKa. And our pKa is equal to the negative log of our Ka. Okay, so the negative log, and our Ka was given in the initial problem. It's 1.9 times 10 to the negative fifth. Our pKa is 4.73. So now that we have our pKa, we plug that into the Henderson-Hasselbalch equation, and we plug in our equilibrium amounts of conjugate base and weak acid. We plug those values in and find that our pH is about 5.32. Okay, this is the process you will follow before the equivalence point. Okay, part B corresponds to at the equivalence point. Okay, and so we started with an initial amount of 0.03 moles of weak acid. Okay, now in part B, we add 0.03 moles of hydroxide. Okay, so again, just like in part A, we want to make enough hydronium to neutralize all of that hydroxide. So if we're adding 0.03 moles of hydroxide, we're going to want to make 0.03 moles of hydronium. Therefore, we want to make 0.03 moles of our products and subtract it from our reactants. Okay, now anytime you are at the equivalence point, at equilibrium, you should have 0 moles of your initial weak acid or weak base, and it will all be converted into product. Okay, all of this hydronium would neutralize the hydroxide added. Okay, so that goes off and neutralizes the hydroxide. And what happens is this conjugate base will actually now react with water to go backwards and form some of our initial weak acid. Okay, so at equivalence point, we see a reverse ICE table. Okay, so our conjugate base will react with water to produce our initial acid plus hydroxide. Okay, now our initial amount of conjugate base here will be the amount of conjugate base that we had at equilibrium in our previous ICE table. Okay, so this 0.03 moles is going to carry over into our reverse ICE table and be our initial amount of conjugate base. Okay, now our change we're going to put in terms of X, so plus X for products, minus X for reactants, and at equilibrium, we will express that amount in terms of X. okay? But this number, 0.03, is in terms of moles, okay? We're gonna eventually want to relate this to KB or Ka, okay? And to do so, we need to convert 0.03 into concentration. That's what that bracket means. And so to do this, we're gonna take moles of that conjugate base, 0.03 moles, and divide it by our total volume. Okay, so in part B, we have 300 milliliters or 0.3 liters of weak acid, and we have 50 milliliters or 0.05 liters of strong base. Okay, so when we divide moles by the total volume, we find that our concentration of that conjugate base is 0.0857 molar. Now that we know this amount of conjugate base that we have at equilibrium in terms of concentration, we can relate it to Ka or Kb in order to solve for X. Okay, and so you might ask yourself, which one do you use, Ka or Kb? And you use whichever one is the, whatever species is your reactant in your reverse ice table. Okay, so in our reverse ice table, our reactant is a weak base. That indicates that in order to solve for X, I'm going to relate it to Kb. Okay, and so in order to relate this to Kb, I actually need to solve for Kb. And I do so by using this expression. Ka times Kb will always equal 1 times 10 to the negative 14th. Now, Ka was actually given in the initial problem, so using that value, I could find that my Kb was 5.26 times 10 to the negative 10th, which would be equal to my concentration of weak acid times my concentration of hydroxide divided by my concentration of conjugate base. Okay. From here, I plug in my equilibrium values from my reverse ice table. Notice that my amount of conjugate base is in terms of molarity, so I use that 0.0857 value, not 0.03. Okay, and I'm going to ignore the x in the denominator and solve for x, which ends up coming out to 6.71 times 10 to the negative 6th, which is equal to my equilibrium amount of hydroxide. Okay, so this value, 6.7 times 10 to the negative 6, is my concentration of hydroxide. So knowing this value, I can actually now solve for my POH, right? My POH is equal to the negative log of my hydroxide concentration, so I take the negative log of this value, and it comes out to 5.17. Okay, now pH and plus POH will always equal 14. So using that relationship, I can find that my pH should be 8.83. Okay. And looking at how many people are here, I think a lot of people have just joined late. If you joined late, if you don't mind signing into the chat using your net ID, I would appreciate it. Okay, so again, this portion, part B, corresponds with past the equivalence point. Anytime you are past the equivalence point, you are going to have a reverse ice table. Okay, now part C. Part C corresponds with after the equivalence point or past the equivalence point. Okay, so the same kind of logic occurs here, right? In part C, we are adding 0.0312 moles of hydroxide. Okay, we figured that out a couple of slides ago if you weren't here for that. Okay, so we're going to do the same setup as before, right? Our weak acid will react with water to produce hydronium and conjugate base. Now, our initial amount of weak acid is 0.03 moles, right? Now, we are adding 0.0312 moles of hydroxide. So ideally, we'd want to produce 0.0312 moles of hydronium. However, we can't, right? We are physically limited by the amount of weak acid that we have. And so what we're going to do is convert all of our initial weak acid into product in order to neutralize as much hydroxide as we physically can. Okay, and so we're going to subtract 0.03 moles from reactant side, add 0.03 moles to product side. So at equilibrium, we will have 0.03 moles of hydronium and 0.03 moles of our conjugate base. Okay, now at the equivalence point, right on our last slide, when we had no amount of initial weak acid and we at equilibrium, and we did have a certain amount of our conjugate base at equilibrium, we did a reverse ice table. Okay, now technically, when we are past the equivalence point, that does still occur. However, doing a reverse ice table and doing all this complicated math that we had to do in the previous problem, that will not affect your answer, okay? So when you're past the equivalence point, does a reverse ice table technically happen? Yes, but it will not change your answer for the pH whenever you're past the equivalence point. And so we ignore that. Okay, way back when we covered chapter 15, I actually did a problem where we proved that. And I don't remember who taught chapter 15 off the top of my head, but I know your professors in a lecture also proved that when you're past the equivalence point, technically a reverse ice table happens, but it won't affect your answer, and so it's not worth it to put yourself through all that extra work. Okay. And so if we don't need to do a reverse ice table, you might ask, how do we find our pH? Right, so again, we converted all of our reactants into products to produce 0.03 moles of hydronium. Right, and in part C, from the initial problem, we are adding 0.0312 moles of hydroxide. So what happens is this amount of hydronium, the 0.03 moles of hydronium and 0.0312 moles of hydroxide, they're going to react and make as much water as they physically can, right? So they're going to react and produce 0.03 moles of water, right? After they make that water, we will have no hydronium left over, right? All that hydronium will be used up to make water, but we will have an excess of 0.0012 moles of hydroxide. Okay, so you find the pH from this portion by taking the excess moles of hydroxide that you have here. You're going to divide it by the total volume from this part of the problem, right? So 0.3 liters, this was the 300 milliliters of weak acid you started with, plus the 52 milliliters of strong base you added. So 52 milliliters is 0.052 liters. And when you do this division, you find that the concentration of hydroxide is 0.0034 molar. Okay. Once you have your concentration of hydroxide, you can find your pOH by taking the negative log of that value, which would come out to 2.47. And then we can use our relationship between pOH and pH, right? They always add together to make 14, to find that our pH is 11.53. Okay. Before moving on, does this make sense to people? I know quite a few people last session, when I asked what to cover, emphasized that they wanted to go through titrations, and some people specified at the equivalence point and past the equivalence point. Does this make a little bit more sense now? Okay, hopefully. People also asked me to go through buffers, so I do have a quick example for buffers, which is the second to last little topic we're going to review tonight. So remember that buffer solutions can resist the addition of both acid and base, right? So H plus or hydroxide. And to have a buffer, you need two components. You need a weak acid and its conjugate base. right? And so typically we will form this through one of two ways. The first classic way to make a buffer is you will add a weak acid to a beaker, and then you'll also add the weak conjugate base, which is often added in the form of a salt. Okay, so the classic example I always use is your weak acid might be hydrofluoric acid, HF, and to that you would add the conjugate in terms of a salt. So you might add sodium fluoride, NaF, right? The sodium we don't really care about there. What we care about is the F minus that we're adding through NaF, right? So if you have HF and F minus, you have your acid and your conjugate base, you have a buffer system. Okay, you can also form the buffer through the partial neutralization of a weak acid or a base with a strong base or acid. Basically, what that means is you form a buffer anytime you have a titration question where you are before the equivalence point. Okay. And so just some other notes about buffers. Doing buffer problems, you can, in your ICE table, you can plug in concentration or you can plug in moles. I tend to typically do moles, but either one will work. For pretty much any buffer question, the Henderson-Hasselbalch equation will be your best friend. And remember that the whole idea of buffers is to neutralize the addition of, sorry, this says weak acid or base. It's supposed to say strong acid or base. Okay, Henderson-Hasselbalch equation here. And then just some last notes, the effectiveness of a buffer. If you have more buffering components, so larger concentrations of your acid and conjugate, that makes it a better buffer, more effective. And then remember that your buffering capacity, right? Every single buffer system can only buffer a small pH range. And we say that that range is the pKa of that acid plus or minus 1. Okay, so let's look through the last example for this evening. Okay, so the beginning of this question is actually going to be the same exact thing that we did for the titration question, about 10 or 15 minutes ago, and part A of that titration question, right? So we're gonna have 300 milliliters of 0.1 hydrozidic acid. It's titrated by 40 milliliters of 0.4 molar barium hydroxide. Is the resulting solution a buffer? The answer to that is going to be yes. If it is a buffer, you add 10 milliliters of 0.41 molar potassium hydroxide to this system. After the addition of potassium hydroxide, is the buffer system broken? Okay, and what that last portion means, buffer system broken, it means is the pH, once you add potassium hydroxide, outside the buffering capacity of hydrozidic acid. Okay, so this first portion, the creation of the buffer through the titration step, I just kind of stole from when we did it, again, about 15 minutes ago, right? We had 300 milliliters of 0.1 molar hydrozidic acid. I'm going to say that that's HA. So we have 0.03 moles of that. Okay, now when we add 40 milliliters of 0.3 molar barium hydroxide, that's like adding 0.024 moles of hydroxide. So that's going to be our change. We'll subtract from the reactants, add to the products. And at equilibrium, we have a certain amount of weak acid and a certain amount of conjugate base. Okay, so because we have an amount of both of these, this is a buffer system. Okay, so now let's actually look at the buffer portion of this. Okay, so because it's a buffer system, we're going to be adding 10 milliliters of 0.41 molar potassium hydroxide. Okay, and so when we do this calculation, this will come out to 0.0041 moles of hydroxide being added. Okay, and so that is going to represent the change in our ICE table. Okay, so our ICE table, I'm going to write the equation. So our weak acid reacts with water to produce hydroxide and conjugate base. And you'll notice that the initial amounts that I input were my equilibrium amounts from the titration step, right? So I'm just going to go back to the last slide for a second, right? This was our titration step. These equilibrium values is now going to be the initial amounts that I use for my ice table when I add this potassium hydroxide. Okay, now I'm adding 0.0041 moles of hydroxide. Now again, the whole purpose of a buffer is to shift equilibrium in order to neutralize hydroxide. Okay, we neutralize hydroxide by forming hydronium. Okay, so if I'm adding 0.0041 moles of hydroxide, I want to create 0.0041 moles of hydronium, which will neutralize all of the hydroxide added. Okay, so that's how I knew to add that number to the product side and subtract it from the reactant side. Okay, if I had this same problem and instead added strong acid, right? If I had strong acid and I had hydronium in my equation, I would have subtracted that value from the hydronium section. Okay, so again, I subtract that value from reactants, add it to products, and now I have a new equilibrium amount of weak acid and conjugate base, right? So that equilibrium, I should have 0.0019 moles of my weak acid, and I should have 0.0281 moles of my conjugate base. Now again, I have a certain amount of conjugate base and weak acid. Whenever you have a certain amount at equilibrium of each of these, you can solve for the pH using the Henderson-Hasselbalch equation. Okay, so that's what I'm going to use. And to use the Henderson-Hasselbalch equation, I need my pKa. Okay, so I take the negative log of my Ka, which was given in the problem. And so my pKa is 4.72. I'm going to plug that value in along with my equilibrium amounts of conjugate base and weak acid, right? So 0.0281 and 0.0019 I'm going to plug in. And when I solve for the pH, I find that my pH is 5.89 after the addition of potassium hydroxide. Okay, now again, remember that buffering capacity is going to be equal to our pKa plus or minus 1. Okay, so for for this acid, right, hydroazidic acid, our pKa is 4.72. That means our buffering capacity, right, it would be able to buffer between 3.72 and 5.72. Okay, now the current pH of our solution is not within that buffering range, meaning that we have broken that buffering system. Okay, which really just means that this buffer, it's just not going to be good at resisting pH changes any longer. Okay, it's only good at resisting pH changes within its buffering capacity. Okay. Any questions on that before I think I have about 3 more slides to go through? Okay. So the last thing I wanted to talk about was water electrochemistry. And so this was the initial slide that I gave back when I went over it. And so I just wanted to, you know, I still wanted to give that to you in case you haven't seen it, if you want to take notes on it. But what I'm going to try to do is break this down on the next couple of slides and try to make what I say on this slide make more sense. Okay, but basically the gist is that when you have when you're doing electrochemistry within water, right? So you have water in your anode and cathode, things can get complicated because water, I say water can be oxidized or reduced, but what really happens is water gets reduced to hydrogen gas or oxygen. Oh, well, yes, water can be oxidized to oxygen gas. I do apologize. Water can be oxidized to oxygen gas. However, on your table of values is in terms of reduction potential. Okay, and so it would be in terms of actually oxygen and protons. Okay, but again, electrochemistry in water gets complicated because water can be oxidized or reduced. Okay, and so let's break this down. Okay, and so what I want to emphasize is that every single electrochemical reaction wants to be spontaneous, right? That's its preference, right? If it's not spontaneous, it needs an input of energy to help it be spontaneous. Okay, and so remember that in electrochemistry, right, a spontaneous reaction has a positive cell potential or a positive E value. Okay, and so here's a general standard potential table that you would see, right? And we do see these trends, right? It says that towards the bottom of the table, we have better oxidizing agents, and towards the top, we have better reducing agents, right? So according to this table, Li plus, lithium plus is the best reducing agent, right? And what does that mean and why? So remember that reducing agents get oxidized, okay? And this makes sense, right? So all of these potentials are in terms of reduction, okay? So if at the top, they are good reducing agents, meaning they get oxidized, right? If it's getting oxidized, it's actually the reverse of these half reactions listed. Okay, so if lithium is acting as a reducing agent, it's going to get oxidized, meaning the half reaction would actually be lithium solid goes to lithium plus plus an electron. Now, when we flip a half reaction, we change the sign on the standard potential, right? So if we are oxidizing this lithium reaction, we're flipping it, and its potential, its oxidation potential, would actually be positive 3.04. Well, if it has a oxidation potential of positive 3.04, that's a really large positive number, which means when we add our two half reactions together and add our E values together, if we have a hugely positive oxidation potential, that's going to help our overall cell potential be positive and therefore spontaneous. Okay, so that's why towards the top of the table, these prefer to be oxidized, right? Because then they'll end up having a really large positive E value. Now at the bottom of the table, these half reactions prefer to be reduced. Okay, now that makes sense because as you can see, as we go further down the table, their standard potential gets larger and more positive as we go down. And again, this makes sense because these are our reduction potentials. And so if they have large positive reduction potentials, that's going to help our overall cell potential be positive and spontaneous. Okay. And so let's bring this back to electrochemistry in water. Okay, so again, at the cathode, water can be reduced, and this is the equation, and it has a certain reduction potential. Okay, if the half reaction occurring at the cathode has a more negative reduction potential compared to water's, meaning it's higher up that standard potential list, then water would be preferentially reduced. Okay, and that's because, again, water's reduction potential would be more positive compared to the half reaction, which means it would, compared to the half reaction, allow the overall cell, it gives it a greater chance to have a positive E value and be spontaneous. Okay. Now, on the contrary, in the anode, right, in the anode, water can be oxidized. Okay, and again, this is the oxidation half reaction for water, but realize that in that table, it's always given in terms of reduction potentials. So this is the reduction potential of the half reaction, and this is how you would see it be written, right? It's just the reverse of that equation. Okay, and so if the half reaction occurring at the anode has a more positive reduction potential, right, which means it's going to be further down that table, right? If it has a more positive reduction potential, it's actually going to have a more negative oxidation potential. And again, remember at the anode, oxidation occurs. And so therefore, in order to help make the cell spontaneous, oxygen will actually be, I apologize, this last portion's incorrect. It would be then water will be preferentially oxidized into oxygen. Okay, so I flipped water and oxygen here. Okay, but basically the whole idea of this is that the anode or cathode, right, water will be preferentially reduced or oxidized if it gives the overall cell a greater chance at having a larger positive cell potential compared to the respective half reactions occurring at the cathode or anode. So no, not necessarily. So the question in the chat says you need to be between negative 0.828 and positive 1.299 for water not to be oxidized or reduced. That is not really true, because that kind of makes it seem like it's all happening in a single beaker, right? And they're separate. When you're talking about the cathode, right, if your reduction potential is higher or more positive than negative 0.828 volts, if your reduction potential of the half reaction is more positive than that negative 0.8 value, then your half reaction will be reduced. Okay? It doesn't matter if that half reaction has a reduction potential of 2.999, right? Just if you're at the cathode, your reduction potential needs to be more positive than this value to be reduced at the cathode. Okay? At the anode, right, if your reduction potential is more negative if your reduction potential of the half reaction is more negative than 1.299 volts, then your half reaction will be oxidized and not water. Okay, so I would not memorize it as your half reactions need to be between these two numbers, because that's not true. Okay, it's at each respective electrode. It just needs to be on the respective side of the reduction potential of water, right? So at the cathode, as long as the half reaction has a more positive reduction potential compared to water, it will be reduced. At the anode, if the half reaction has a more negative reduction potential compared to water, it will be oxidized. Okay. Okay. And so that's all I have for tonight. That's the review. So I am happy to stick around and answer any questions. Just my last kind of comments. So I probably will not have time, especially trying to make some challenge problems and practice problems for you guys, to record a new video going over all the pertinent material for your final. However, I did record a video last year, and so I still have that video, and I will upload that link into Husky CT. The material is extremely similar between last year and this year. All the main material's the same, and so it's about 2 hours, I think. And so that could be a good place to start for content review. Okay, if you prefer a content review that's a little bit more catered to this year, I honestly recommend you going back to all my individual review sessions before exams, right? So every SI, the Wednesday before an exam would be content review from those respective chapters. Okay, so if you prefer to do that, I think either of those are probably your best bet. In terms of practice questions, I'm hoping to make about 30 practice problems for you guys. And so this comes out to about 3 questions from chapters 11 through 18, which was, oh my God, I don't even remember what chapter 11 was. That's colligative properties and molarity, all that stuff, through chapter 18, electrochem. So of these 3 questions, at least one will be multiple choice, and I will probably try to make that some theoretical or hypothetical understanding question to really test kind of your knowledge. And at least one will be long answer, right? And those long answer ones will probably have multiple parts that really test your ability to do these calculations for the key topics within each chapter. Okay, chapter 19, which is nuclear chemistry, you haven't been tested on yet, and so I'll try to make about 6 questions from that chapter. And so my goal is to upload these questions around midday by Sunday. If I can get it up sooner, awesome. But I'm definitely not going to make promises. Making 30 problems and making sure that they work out is definitely extremely time consuming. Okay, and then my goal would be to have my solutions and kind of talk my way through them in a video that I would upload hopefully Sunday night, but if not, I would record it right after work on Monday. So it would be probably upload around 4, 5, 6 o'clock Monday night at the latest. In terms of, some people want to know how to kind of study for the final, and what I want to emphasize is your finals probably, and your professors probably know better, it's probably right around 50 questions, okay? 50 questions from 9 chapters, okay? So there's only going to be about 4 or 5 questions per chapter, okay? And so your professors are going to be asking for the main points of each chapter for the most part, okay? It's going to be the main ideas, main topics, main equations, and very, very key theoretical points that they ask about. It's not going to be all those small nitty-gritty details, right? Pretty much everything that you see on the final, you will have seen one way or another across your respective exams throughout the semester, okay? So if you're getting really worried about this tiny itty-bitty detail that you don't remember, I mean, definitely study it. Everything in these chapters are fair game, but again, on average, they're going to ask 4 to 5 questions per chapter. And so for the most part, they're going to be rather broad questions. Okay, so just kind of keep that in mind while you're studying. Okay, and so I'm just going to stop the video here, but if people have any questions, I'm happy to stick around and answer questions. And to those of you that are going off, best of luck studying for your final. Actually, can somebody put in the chat, it is Wednesday morning, your final, correct? It's almost always Wednesday morning at 8 a.m. I'm kind of under that assumption because that's how it's been for at least the last 6 or 7 years. Okay, it is, perfect. Okay, so my general timeline to release this stuff is relatively good. All of a sudden, I didn't want it to all of a sudden be Monday morning without me knowing. Okay, but best of luck studying to you all. And yeah, again, if there are any questions, I'm happy to answer them.